Hello everyone, welcome back. Today we are going to talk about capacitance. First of all, what is capacitance? To understand it, we need to begin with the electric field. Imagine two charged particles. One is positive, the other is negative. The electric field goes from the positive particle to the negative one. The negative particle's field direction is inward, while the positive particle's field direction is outward. We already explained the electric field in the previous video. Now, let's think about an electric field on a molecular scale. This object contains many charged particles, and we can represent these small charges by dq. The object will be positively charged, and the other one negatively charged, again containing many charged particles. The total charge is plus q. The electric field lines between these two objects look like this. At this point, we can ask, how much charge does this object actually hold? The answer is capacitance. It's like the capacity of the object. Formally, capacitance is defined as charge divided by potential difference. And the potential difference is actually joule per coulomb. Now, let's move on to the second part. How does the capacitor actually work inside a simple electrical circuit? Imagine a very basic circuit connected to a battery. In this system, electrons always move from the negative terminal of the battery toward the positive terminal. This is the natural flow of electrons. But here is the important detail. The electric field direction is opposite to the electron movement. This is something that often confuses people. So always remember, while the electric field points from positive to negative, the actual flow of electrons is from negative to positive. Now, let's say we decide to add a capacitor into the circuit. So, what is a capacitor made of? A capacitor is basically formed by two conductor plates placed parallel to each other. These plates are just like the charged objects we discussed in the beginning of this series. One plate becomes positively charged, and the other becomes negatively charged. When we connect the capacitor to the battery, the situation becomes very interesting. Electrons start to move, and we can describe their motion step by step. Conductors have a very specific property. Electrons inside them can move freely. This means the charges are not fixed in place. They can travel under the influence of an electric field. So, on the negative plate, electrons accumulate. Their direction of movement is inward, into the plate itself. Because the battery pushes them there, the plate becomes negatively charged. On the other hand, the positive plate loses electrons. Electrons move outward from this plate and travel into the connecting wire, moving toward the battery. As electrons leave, the plate becomes positively charged. Electrons move from the negative terminal to one plate of the capacitor, giving it a negative charge. At the same time, electrons leaving the positive plate cause that plate to become positively charged, because the electrons are negatively charged. And in their absence, the plate is left with a positive charge due to the protons in the atoms. This 3D visualization makes it easier to see how charges distribute across the capacitor plates and how electrons flow in the system. This process continues as long as the battery is connected. The battery pumps charges, increasing the amount of stored charge on both plates. The more electrons that accumulate on the negative plate, the more electrons are removed from the positive plate. Because of this, the potential difference between the two plates grows continuously. Now here is the key point. This separation of charge does not happen randomly. The charges on the plates create an electric field in the region between them. The field points from the positive plate toward the negative plate. This is exactly how the capacitor stores energy. Not as free charges moving around, but as an electric field established between two conductors. And this is the definition of capacitance in action: the ability of the capacitor to store charge per unit potential difference. Let's also remember the units. In the SI system, capacitance is measured in farads. 1 farad means 1 coulomb of charge stored per 1 volt of potential difference. Now let's move to an even more interesting concept in capacitors: the dielectric constant, usually written as epsilon E. So, what exactly is epsilon? Epsilon is a physical property of every material, and it describes how the material reacts when placed inside an electric field. Let's repeat the basics to make it clear. In conductors, electrons are free to move. They can drift under the effect of even a very small electric field. In contrast, insulators, or dielectrics, do not allow electrons to move freely. Their electrons are bound tightly to atoms or molecules. Let's go back to the capacitance formula and check the role of potential difference. In this formula, we see a constant called Kc. Co is necessary because it converts coulomb per meter into joule per coulomb, which is consistent with the definition of potential difference. And as we already know, potential difference is equal to electric field multiplied by distance. From this relationship, we can rewrite the capacitance formula in terms of the electric field. In this process, the charges cancel out, leaving us with an expression that directly connects capacitance, area, distance, and epsilon. If the conductor is spherical with radius d, the formula becomes C equals 4 pi epsilon r, and from this formula, the charge density can also be calculated as coulombs per square meter of the sphere's surface. Now, let's take another look at potential difference, but this time from the perspective of electric field and surface charge density. Potential difference equals electric field times distance. This can also be written as charge times distance divided by dielectric constant times area. When we simplify this relationship, we get the well-known formula for a parallel plate capacitor. C equals epsilon times HOI divided by D. Here, A is the surface area of the plates, and D is the distance between them. This clearly shows us something important. Here, in terms of the electric field, the distance between the plates is the most critical factor. To make this idea more concrete, let's use a simple everyday example: a computer keyboard. Have you ever wondered how the keyboard detects that you pressed a key? Underneath each key, such as the Z key, there is a small capacitor. The capacitor has 2 plates separated by a thin layer of insulating dielectric material, often elastic plastic or rubber. When you press the key, your finger pushes the plates closer together. In other words, the distance between the plates decreases. According to the formula, when the distance decreases, the capacitance increases immediately. This change in capacitance causes a change in the electrical signal within the circuit. The change is detected, processed as an electromagnetic signal, and the computer interprets it as the letter Z being pressed. So the keyboard is an excellent and memorable example. To make it clearer, here you can see the figure where I modeled the keyboard. A 3D model of a capacitor can help you understand how it works. In the system I modeled, you can observe the direction of electron movement. That shows how capacitors and dielectrics work together in real life. It turns an abstract formula into something tangible that we use every day. Let's start with the structure. If the conductor is cylindrical, this represents the positively charged inner plate of the capacitor, and we denote its radius as lambda sub. The outer conductor plate surrounds it, and its radius is b. Both plates have the same length. To analyze the system, imagine a small conductor moving inside the other. An important detail is that between the two conductor surfaces, there is an insulating material called a dielectric. This insulator ensures that the charges do not directly touch each other. Now, let's look at the capacitor from above. The inner plate has radius A, and the outer plate has radius B. The electric field lines originate from the positively charged inner plate and point outward. On the other hand, the surface of the outer conductor is negatively charged, and the dielectric sits between these two plates. Next, we consider the potential difference between the outer plate at radius B and the inner plate at radius A. The potential difference is related to the electric field. Since the radius changes, we must consider a small differential element of radius, which we multiply by the electric field. By integrating this differential expression from radius A to B, we get the total potential difference of the capacitor. Let's think about what changes in the system. The radius can vary, but we need to consider two radii along the same line, which is also the line along which the electric field exists. This means the radius and the electric field are interconnected. Here we introduce lambda, the charge density along the length of the cylinder, and r, which is the distance from the center along the radius. We can express the electric field in terms of lambda and r. Lambda represents the charge per unit length. The potential difference between die and A depends on the geometry of the capacitor plates. The inner plate has radius A and the outer plate has radius B. Now imagine looking from above. The circumference at distance r is 2 pi r, and we want the total electric field around the full circle, not just along a single line. This is why the integral includes the constant 2k sub e, where k sub e is Coulomb's constant. Here, 2ke times lambda remains constant because lambda represents the charge density. After performing the integration, we get a logarithmic result, the natural logarithm of r. This shows that in a cylindrical capacitor, the potential difference changes logarithmically with radius. Finally, the capacitance of a cylindrical capacitor can be written as C equals Q divided by 2ke times lambda times ln of B divided by a set. This formula gives the capacitance in terms of the charge density, and the geometry of the cylinder. One important thing to remember, the differential radius in the integral is not just the difference between A and B. It represents an infinitesimal change in radius, which is key to calculating the potential difference accurately. So, in summary, cylindrical capacitors work by having two coaxial plates separated by a dielectric. The electric field varies with radius, the potential difference changes logarithmically, and the capacitance depends on both the charge distribution and the geometry of the plates.